We'll go ahead and turn it over to Alessandro for lecture 3.
Okay, thank you. I guess I have to share my screen. Hmm. So I have to confess I didn't have a lot of time to read this one because this week has been completely crazy with teaching and other things. But I hope it's gonna be fine. Um, so what we're doing today is to actually get to the computation of the dim on the image of the map we considered. So let's recap what the map does. We have our objects that look like this. Then a little bit further down. Actually, let me use one example from the paper. So I know when I'm not messing up anything. Um, so with four, four again, four again, one, then four again. So I have to go down a little bit. That's 17, which is extremely suspicious. Okay, sure, this is fine. We have a diagonal here. The path goes below at some point, but that's fine. We don't really care. We have some labeling. 2, 4, 5, 2, and then I'm using, say, red for big labels. I'm skipping the other lines. I hope it's fine, but I can add them if you want. Yes, that's 2, the 1, 1, 2, 3. So in this picture, we have m equals 5, n equals 3, I would say. No, sorry, n equals 4, k equals 3, n equals 2. Yeah, n equals 2. So the width is m, the height is n plus km, which, well, is 17, so we're happy. And how's the labeling? Labels, well, the blue labels can be anything, really any natural number, we don't care. The condition here on K, I mean, we're restricting to a subset of these objects in which like the labeling with the big labels is one of the fixed points of the bijection we showed last time. So in practice, that means that the big labels can go up to K, which is 3 in this case. And they have to be placed in a very specific order, meaning that, well, meaning something that we're going to show in a second. So this is the height. I never get the H and the T right. H with, okay. So let's also recall the thing that we called ENS representation. We had that for decorated paths, but we can like do this on the image here. So what we do is we start as before, going up 4, and then after each column, we go down by k. I'll use, say, orange for this. And we have one horizontal, we go up 4, we go down by 3, 1, go up 4, go again down 3, here we go up 1, we still go down 3, and then 1 here, up 4, and then down 3 again, and then 1 horizontal. So now the slope here is now, I mean, the height is just n, the width is m, and our bijection, which is not a bijection at this stage, but it doesn't matter. I guess I can add back the labels as well. I'll draw them on the right because, well, there's not enough space on the left. But this is the usual labeling of the north steps of the path. 3, 1. Okay. 1, 2, 3. We have yeah, here. All right. So what our map does at this level is to delete the steps, like the red steps and the matching orange south steps. So what we have after applying our bijection is this goes up 1, right 1, up 2, down 1, right 1, up 1, straight 2, up 1, no, down 2, yeah, here, sorry, down 2 here, straight 1, up 1, right 1, right. So we keep the same width and height. The only difference is that we have a lot less north steps and, well, and south steps, I guess. And this, if we want to draw it like in the usual way, becomes this garden here. So basically, whenever we have a south step, we transform it into a decorated fall. This. No, line is not straight at this point. It's this wobbly thing that goes up with slope 1 under decorated falls and slope n over m in columns without decorated falls. Okay, and I guess we can also like keep the labeling here. So it's gonna be 2, 1, 4, 5, 2, and the same goes here. Now we can draw the labels in the usual places. And to remember the red labeling here, what we do is essentially to label the south steps here with the complement of the red labels in the same column. So that's gonna be 1, and here we're gonna have 2 and 3 decreasing, well, going down, well, increasing going down. So these decorations are gonna correspond to 1, 2, and 3. And all over here, we have the convention that, well, 1 doesn't 2, blah, blah. And then the red numbers are bigger than everything. I guess, like in the paper, I just overline those, but since I can use colors here and it's, well, and they're distinguishable, I can avoid the bars and make it a bit easier for me to draw everything, but like, okay, red numbers are bigger than blue numbers. Okay, so this is the map. And once we restrict, well, the point is that when we apply the skewing operator, the Schur function skewing operator, we show the sign reversing involution that basically gives us as fixed points only the things here in which these decorated falls or these south steps here are labeled from 1 to k from the farthest to the closest to the diagonal. So we can pretty much ignore the labels once we um, restrict to the fixed points because there's only one valid labeling of the decorated falls. So you can pretty much ignore the labels here. They don't really matter. So what we want to do is to compute the dim of these guys here. And we want our bijection to be statistic preserving. So the dim here or here, whenever they're the same thing, must be the same as the dim on this object here. So this is the whole point, and this is what we're going to show today. The some of you might notice that I never said what the dim is here. Well, I gave some overview in the first lecture, like I said something, but I didn't go into details like on what's the actual formula for the dim here. But it doesn't matter because it's gonna like pop up naturally once we apply this bijection here. Pretty much it's gonna be the image of the dim here. I'm gonna get something here that we call the dim, which looks a lot like the dim we expected to find. Most importantly, it extends both the dim on, well, square decorated objects and non-decorated rectangular objects. So it's a like legit choice. It's actually a generalization of the dim for the rational shuffle theorem and for the Rice version of the delta theorem. And yeah, we're gonna care about that a lot. So I guess we want to start by saying what the name here is. So we have a bunch of factors. Well, for a generic rectangular path that's taller than wider, so well, okay, obvious remark. If k is at least 1, the path is taller than wide. I'm not sure about the grammar of this sentence, but I hope it's fine. What I mean is the height is larger than the width. Okay, so for paths with this property, we have the temporary dim, which is the number of pairs ij such that ai less or equal in lexicographical order than j less or equal lexicographically ai plus 1 I, and wi less than wj. So the label of the step index I is smaller than the label of the step index j, and ai is the horizontal distance between the starting point of the step and the main diagonal of the path. It can be negative. In this case, it is negative. It can be a rational number. It doesn't have to be an integer. It can be pretty much whatever. It's AI. It's a rational number. We don't know a lot more than that. Um, but in our case, we can do something very slightly different. This is the same. If instead of AI, place VI, what we call VI, and here I have VI plus K plus N over M. So what I'm doing here is saying, okay, instead of looking at the horizontal distance, I'm looking at the vertical distance. The inequality stays the same because, well, all these triangles are similar. So if this is less than this, then this is less than this. So we have the same inequalities, but I have to change this one here with the appropriate number, like in the, sorry, I got it the other way around. I got it the other way around. Yes. Yes. All right. Sorry. This is K plus N over M. It's a slope of this path here. Well, I mean it's M plus sorry, N plus Km over M, which is K plus N over M. And well, by definition of slope, the horizontal distance increases by that number if the vertical distance increases by 1. This looks horribly wrong, doesn't it? Yeah, I think it's fine. I think it's fine. All right. Mine. This doesn't care. Okay. Okay. I think this is fine. Let me just check for sanity, but it should be okay. Yeah. Right. Okay. And then we have a correction, which we showed in the first lecture to be the number of pairs of steps in the path above, say, have an example here. I don't know, maybe this one, hopefully. Such that if I draw the lines parallel to the main diagonal, I think that's okay. The vertical step projects entirely within the horizontal step. So maybe let me draw another picture here. We have some horizontal step here. We keep the right endpoint, but not the left endpoint. We have some vertical step somewhere here. And we want that if we trace lines that are parallel to them in diagonal from the endpoints of the vertical step, they all fall inside the horizontal step. And this is what we call the dim correction or CDIM. So is number of such things, I guess, with the plus sign. Well, parentheses of this pattern. And dim of this thing here, if I call this pi, let me call it pi tilde, pi is gonna be the image, and then the dim of this thing here is the temporary dim of this gadget plus this correction. And actually, there's another thing I have to say because this path can go below the main diagonal. So actually, I have another term that's the number of steps such that AI is less than 0. It's the same as in the square path conjecture. So we got to consider this correction as well. Okay. Um, what we would like to do to more easily interpret these summons is to split this part here, depending whether or not the label associated to the north step is red or blue, is big or small. And if we do another like simplification again for sanity, let us call V calligraphic V, which is horrible to write in pen and paper. That set of vertical um, small labeled steps of pi tilde. We are using this interpretation here again to interpret more easily the things. H,
Can I, can I ask a
yeah,
question?
sure.
Um, is there a way to reverse this statistic nicely? I guess, like,
Uh,
since your path is crossing the diagonal, sometimes it's not obvious to me how to do the same thing as what Maria and Eugene and I did, where you have like you're like counting pairs of cells where one of them
mhm.
is like below the path, something like that.
Uh, I'm not sure what you mean. I mean, this thing can happen even if this guy is below them in diagonal. Like I mean, these are parallel to them in diagonal, but they can be like below them in diagonal. So we count these things the same way.
Yeah,
I'm not sure
I'm
if
just asking how is there a nice way to reverse the statistic?
um I mean a nice way to like see what this guy hit is.
Yeah, like the in the in the rational shuffle theorem case,
Hmm. Hmm.
when you reverse, you have like Kaplan, which is like your correction terms.
Ah,
But
you're right, it
then,
does like the maximal TDINV minus.
yeah, but then when you reverse everything, this like Pafton, the arm and leg Pafton thing turns into counting pairs of cells.
Hmm.
So I was wondering if you can do that kind of thing for these statistics.
I mean, this is what's sort of happening. I mean, this condition here, I'm not sure what I mean. Like this condition here is the one, it's the same as like, okay, you look at this guy, you look at this guy, and then check if the arm and the leg have like the right inequalities. And then this gives you too much because you're also adding like all the like the max TDINV. So you subtract the you subtract it, and then what's left is this correction here. I like it a bit better than like the version with pathinv plus tdinv minus max tdinv. because it's a bit more direct. Like your some, well, they're not all positive because sometimes, well, not in this case, but like in if you have a generic shape, this might appear with a negative sign, but well, not this, like the converse. Um, but I think this way is a bit easier for the argument we're gonna make.
Okay.
'Cause- I don't know. I'm not sure. I mean, I don't think this is worse than the other one. It's not great, yeah, but
Okay, fair enough.
yeah, for our purposes, this worked a little bit better, but yeah, they're equivalent. So okay. Yeah, so we call H the set of horizontal steps, Y, and I think we call B this stuff here. Then I think we had two more things, which is D is the decorated south steps. And this is non-decorated south steps. Right here though. So if I call Hilda this guy, I mean, I'm using the same letter for like this and this. It's a bit of abuse of notation, but yeah, there's a bijection, and I think this is a bit easier. In this case, the bijection is a lot easier here because what we do is just to delete these guys and these guys, and the rest gives you pi, where pi is the image here. So this guy here, I call it pi. In general, I'm using pi for the objects. I hope I'm not messing up the notation. Yeah, pi for the objects for this decorated rational shuffle theorem, and pi tilde for the objects of the non-decorated, like the original rational shuffle theorem. Okay, so with this notation here, we can split this gadget into four different terms, depending again if, well, this step or like the step below them in diagonal, if we count this gadget here, is has a big or a small label. So let us call C tilde S set of pairs ij, where I is vertical, J is horizontal, J is less than I, meaning it comes before I in the path. Now again, I'm doing a slightly different thing than what people are used to, because normally you just like index vertical steps. So if I write, like, if I take I equal 5, then it's gonna be 1, 2, 3, 4, 5. It's gonna be this step here. But again, for us, it was a lot more convenient to just label all the steps of the path. So from now on, if I say I equal 5, I'm meaning this horizontal step here, not this vertical step here. I mean, again, there's obviously a like correspondence. You can just restrict to the corresponding subset and relabel and whatnot. But it's a lot easier if we do it this way. So this is gonna be the fifth step, and this is gonna be the sixth step. So when I write this, I just mean the ith step is after the jth step. That's exactly what that is. And this is the condition. So the condition here, what is this saying? It's saying, okay, when I start translating the main diagonal, first I hit this point here, then I hit this point here, then this point here, and finally this point here. So if I do like vertical translates, then I'm just saying like what's the inequality between the vertical distances of these points. And since we call vi the vertical distance between the endpoint of a step and the main diagonal, we use the same notation for horizontal steps. What we are saying is that vj is less or equal than vi, because again, we take this here, the right point is included, so if they are on the same translate, this is okay. So we have this weak inequality. And well, I guess what I have to write is vi plus 1, meaning the distance here, is strictly less than the distance here. So this is vj plus the slope, which is k plus n over m. But then I can move this one like to the right and just write this. And then we do the same for the big steps. It's exactly the same thing. It's the same conditions, same inequality, same everything. I already spent half an hour for this. Amazing. Except the vertical step has a big label. That's the only difference. And then we do the same for the steps below the main diagonal. So BS and BB, which is I in B, such that VI is less than 0. And again, it's the same if I use AI or VI. I mean, if we're below the main diagonal, both the horizontal and the vertical distances are going to be negative, so it's exactly the same condition. And here, again, it's the same. So the sum of the cardinalities of these sets here is our dim correction. And this is the only thing we care about. Well, not really, but it's one of the things we care about. We have to do sort of the same for TDIM, the temporary dim. So the attack relations here. Again, we're gonna split them in 3, depending on like whether it's involving just 2 small labels, 1 small label and 1 big label, or 2 big labels. I guess I'm going to do that later. Or no? Well, okay. We also care about distinguishing whether, like, okay, the small labels we don't really care because if we have an attack relation, if we have a temporary dim that's involving 2 small labels here, we're gonna have exactly the same contribution here because the condition is the same. Like the vertical distances here, they're all the same as here. We just deleted steps. It's the same figure. So if we have a diagonal inversion here, we have a diagonal inversion here, and vice versa. They correspond exactly to each other. So we only care about the ones between big labels and themselves, and big labels and small labels. And we are gonna distinguish the ones in which like depending on which one is on the right. So, and which one is on the left. So we call F S. Well, I guess this is in the other R, but fine, probably. Down arrow. The sets of pairs of steps. I is vertical, J is big, J is less than I, and I attacks J, meaning we have like the usual inequality. This, where is it? This inequality here. We just like write it as I attacks J. Just to avoid, I mean, we're gonna use this a lot, so it's convenient to have a shorthand for this series of inequalities. And notice we don't really care about the labels here because we know the label of I is gonna be less than the label of J because J is big and I is not. So here we're counting like attack relations in which the small label comes after the big label. We have this condition J is less than I. So that's why we have this arrow here. Here we have the small label attacking the big label from the right. Analogously, we call FB with the same arrow. The same thing, except now both labels are big. So we have J less than I. Now we need the condition Wi less than Wj because they're both big. They can have either inequality. 9 attacks J. And finally, the attack relations in the other way around. Now I can be whatever, be big or not. J is big because now we have Wi less than Wj, so we're looking at the attack relations in the other way around. We need to, again, to write this because if I is small, then we don't care, but if I is big, then we need to specify this condition. And again, I is J. All right. So the div of this object here is the temporary div of this object here plus the cardinalities of all these sets. Right, these ones are counting the pairs of steps like this. These two are counting the pairs of steps, well, the steps below them in diagonal. And these three here are counting the temporary div between either small labels and big labels or big labels with other big labels. So the only thing that's missing is the div between small labels and themselves, but we don't care about that because we have it there as well. So this, I mean, we don't have to consider it. We're gonna find it back here and it's preserved. We don't care. And we want to see what happens to all these things when we apply a bijection. This is extremely non-obvious. Well, I mean, this is going to be somewhat preserved because we have B and H here, but all the stuff that involves B, so this term here, this term here, and all the terms here, we cannot recover them from immediately from the path. Like something's happening, the big steps are disappearing, so we have to recover them in some other way. So I guess we're done with the preliminaries. And we can show a bunch of things. Another thing we're gonna mention, well, I'm gonna name, is the half lines starting from any step and like going back. So if I look at this picture here, I can look at any step. Well, maybe I can copy it and make it a little bigger because otherwise it's hard to see. It's fine. It's horrible, but I guess it's okay. Right. So for any step here, I can draw the line starting here and going parallel to the main diagonal, the half line going backwards. And we're gonna care about how these lines intersect things. They're gonna tell us what the dim is gonna be in the image. And well, another thing we can do, and it's also gonna be relevant, is like in between this and the step in and the path in which we delete all the big labels and all the corresponding steps, we have a bunch of intermediate paths that we can obtain just by deleting like one label each time. And it's gonna be a little bit more convenient to like consider them because we can see what happens when we remove one label after the other and like simplify our arguments a little bit. So let us call how do I call them? Phi in some a bar. It's the path obtained from phi tilde by removing all big steps in label strictly greater than a bar. So well, so pi k bar is gonna be just pi tilde, and pi 0 bar is gonna be pi. All good? Okay. So one very obvious thing is, well, let's start from the easiest of these, this gadget here. This is the easy one. We have that if I is a big label, then I contributes to this gadget here if and only if Li starts below the path. That's pretty much obvious, right? So if the intersection of this line here, well, now I don't have a good example in this picture because all the big steps are above the diagonal. But if I have one below, the condition is the same as the line intersecting the y-axis in a negative coordinate. So they contribute only if like they start below, well, that's immediate. Okay. um, slightly less obvious thing. Okay, so we're gonna want to interpret all these things in terms of these lines because, well, later on, I mean, it's gonna be clear. Okay, this proof is messy, and as I said, I didn't prepare very well today because I had a very intense week, but we're gonna use it later. And then, okay, slightly less obvious statement. Maybe I should name these things. Whatever, doesn't matter. So if I have a pair ij in v e times b, this is in f upright arrow if and only if. What's the condition? The condition is I is in pi wj. Well, this is the same as saying I is less than j. Wi is less than wj. And Lj intersects I. So why is that? Well, what does it mean for Lj to intersect I? Now we need a decent example. I hope I have one. Maybe I don't, but what's the attack relation, right? So what does this mean for I to attack j, knowing that I is less than j? Let's go back to the condition. Well, it's this condition really, without the one. This condition really. We're saying that the vertical distance between j and the main diagonal is between the vertical distance of I and the vertical distance of I plus 1. So if I draw the line parallel to the main diagonal starting from the bottom point of j, when is this going to intersect step I? Well, if it intersects step I, do I have a good, maybe this is a good example. This one here should intersect this 2 here. This is the step. So we're saying that this distance is less greater than this, but less than this, which is this plus 1. So this is exactly this condition here. And the other conditions are fixed because, well, the like I belonging to pi j bar is saying this, and the attack relation is the intersection. Okay. So vaguely less, well, now the first non-obvious thing is I didn't say what a lot of these things are. Well, yeah, I mean, I didn't say what the dim in the image is, but gonna see it. And what I want to say is that the number of intersections of lines Li and steps in H union the union S. Yeah, draw the S this way. Yeah. Belonging to pi I bar, meaning the label associated to the step here, if any, is less than I, or for stout steps, like the corresponding north step has a label less than I. summed over I in B is counted by this number here, which is the cardinality of C tilde B, which is the step, remember, the thing counting the patterns like this involving big labels minus the cardinality of FB down arrow, which is this thing here. So the diagonal inversions between big labels and themselves when the small label is on the right, plus what we call C star, the cardinality of C star, which I didn't define yet, but it's one of the terms that's appearing in the div of the image, and it's counting patterns like this. So C star is the number of patterns. 8. This we have one decorated step. Well, I guess we can draw it in the ENS representation. So we have a south step that's decorated. We consider it again empty above, full below. And this is crossing either some horizontal step, sorry. Yeah. We have the projection of the left endpoint of either an horizontal step or another decorated down south step. In the classical representation, what's happening is that we have our decorated step that's now horizontal, and we have any other step here, can be decorated or not. And again, we take the endpoint, and this crosses the decorated step. So this term, the number of patterns like this, is going to appear as a term in the div of pi. And we can relate this quantity with these two quantities by saying that the sum of these things is the number of intersections like the ones I mentioned above. I guess we're gonna see this and then stop for today. Not sure I'm gonna see this today because the proof is pretty long and we have like 5 minutes left. Yeah, no, maybe we stick with the statement today and we prove it next time because it's, well, relatively long proof. I'll mention one last statement maybe before quitting. So we say what we're gonna prove next time is that, well, the other statement I'm gonna prove is that, yeah, again, I didn't say what these things are, but it's gonna be relatively obvious. Okay. So these two I already mentioned. This one and this one. And this C plus and C minus are just the analog terms in pi. So the number of patterns like this and the number of patterns of the other like shape. Let me draw them correctly, check just to Again, not say anything especially stupid. Um, so in the image, at least in the, well, as I said, this thing can only happen if the path is taller than it's wide. But when, as I mentioned in the first lecture, if we have a decorated path, then we sort of glue together horizontal steps with all the decorated folds that appear below. So our C plus, I guess this counts with a negative sign, was it? Well, whatever, I'll fix it if needed. um, so C plus is the classical thing. So horizontal steps that project onto a vertical step. And this can only happen if the path is wider than its tall. But then we can also have the other thing, which is things that project onto something like this. Have a bunch of decorated steps, and then this step fall anywhere in this long streak. And these contribute positively to the div, these contribute negatively to the div, but they both appear when we compute the div of pi, of the image of our map. And these quantities, I guess, well, I guess I can write, if I write it this way, maybe it makes a little more sense. Yeah, sorry. So these, sorry, yeah, I made a mistake here. This appears with a negative sign. So this term here appears in the div of pi tilde. This term here appears in the div of pi, and they correspond to each other. So we're gonna delete these two using these two. And then again here, well, this term appears negative with a negative sign in the div of pi tilde, because this should appear with a plus, but we have a minus. This should appear with a minus, but we have a plus. So this plus this is the difference, right? Like we have to move this on the other side of the equal. So this plus yeah, so this thing minus this is going to be this term that appears in the lim of pi. So we have to see how this contributes to the lim of pi. That's pretty much the idea. Yeah, okay. We're gonna go into details next lecture of the proofs of this and this statement. And then we're gonna like show actually all the terms of the div and see how they sum each other, how they correspond to each other, and finally conclude the proof of the, well, of the equality. I think one extra lecture is gonna be enough, but only time will tell.
Okay. Well, let's thank Alessandro for another great one. And so lecture 4 then will be on Tuesday. Are there any questions
Yeah.
before we adjourn for today? Okay. Well, we'll look forward to hearing more of the
Yeah, I guess
details of this
today, yeah,
incredible
was
formula. Uh, Jesus. Wow.
I guess today was not very exciting because it's just listed things and say, well, some of them appear on one side, some of them appear on the other. But yeah, this proof is just a long computation. It's not very exciting. It's just like very demanding, but it's a
In
bit
English,
boring.
we have this phrase, it is what it is.
It is what it is.
This is what it is. Okay. Yeah. So any other comments? Okay. Well, so long, everybody. Well, oh, thank
All right.
Alessandro again. Yeah. And
Thank you.
see you next week.
See you next week.
All right.